We're going to talk more about indeterminate limits because if you noticed in our notes yesterday, we never talked about the forms 1 to the infinity, infinity to the 0, or 0 to the 0. Algebra is not really going to help in these cases because there's no way to make exponents not be exponents algebraically, but we can use logarithms. So as long as we start with a continuous function on the domain, then taking the log of that function will still allow it to be continuous. So by making the log a product, so bringing the exponent out front, we'll be able to rewrite that as a fractional form and then use L'Hopital's rule. We can then find the limit of the logarithm and exponentiate to reveal the original function's behavior. So that's kind of in words what we're going to do, which sounds kind of confusing, but let's look at some examples. It's not as bad as it sounds. It does take some notation issues that you have to follow carefully, and if you don't use them, I will take off points and you will not get credit on the AP exam. So you need to make sure you follow my methodology for setting it up. Okay, so if I plug in infinity here, I would get 1 plus 1 over infinity, which is 0. So 1 plus 0 is 1 to the infinity. So that is one of the 7 indeterminate forms. So in order to deal with this, we have to use logarithms. So the first thing I have to do is I have to redefine the function as 1 plus 1 over x to the x. Then, and we'll shorten this up a little bit as we move along, but because this is continuous as x gets really, really big, as I'm going to positive infinity, then I can take the natural log of both sides. And I'm going to leave some space in front of the left-hand side here because now my problem is taking the limit of this function. So I'm going to put the limit out in front because that's actually my problem. Okay? So now I'm going to work with the right-hand side. I'm not even going to evaluate what that is at this point. I'm just going to rewrite it. I'm going to say, okay, that's the limit as x approaches infinity. And I can bring the x out front. So it'd be x natural log 1 plus 1 over x, using my log rules. I'm still not going to evaluate that because I knew that I had this indeterminate form of 1 to the infinity to begin with. So I'm going to make it algebraically nice before I do anything. So that's going to be the limit as x approaches infinity of the natural log of 1 plus 1 over x. And I'm going to put this x in the denominator, so I'd have to write that 1 over x. Now, I can plug in infinity. And when I do that, I have the natural log of 1, which is 0, over 1 over infinity, which is 0. And that is a form that I can use L'Hopital's rule with. So, that would be the limit as x approaches infinity of, okay, so now I take the derivative of the top. Well, it's a natural log. So that means it's whatever it's the natural log of on the bottom, and the derivative of whatever comes out after the natural log on top. So it's really just the derivative of that because the 1 goes away. So it'd be negative 1 over x squared. Over the derivative of that, which is also negative 1 over x squared. So rewriting, I have the limit as x approaches infinity of negative 1 over x squared over 1 plus 1 over x times, now I'm going to flip and multiply the denominator, negative x squared over 1. Those x squareds and the negatives will multiply out, and I'll be left with 1 over 1 plus 1 over x times 1. If I plug in infinity now, I get 1 over 1 plus 0, which is really just 1. Now, here's the catch. I didn't want the natural log of the function, I want the function, so I have to e both sides. So when I do the e of this side over here, which is why I left everything on the right, I end up with the limit as x approaches infinity of f of x. And I defined f of x to be that, which is my original problem. So this limit is e to the first, or e. So you can possibly see why notation is very important by working this out here. Okay? Let's look at another example. In this one, we're approaching 0 from the right. So that means I would have 0 to the 0. That, again, is one of the 7 indeterminate forms. So I'm going to set this up the way I did the other one. I'm going to move over here a little to the left this time. Okay, so f of x will be equal to x to the x. So I can take the natural log of both sides. And actually, I can go ahead and bring that x out front, and I can put the limit all in one step. So it does save some writing to do that, which I know a lot of you won't want to write out multiple steps. Okay, so working the right-hand side, again, I'm not going to evaluate until I rewrite. So that's going to be the limit as x approaches 0 on the right of natural log of x over 1 over x. And if I plug in 0 to the right, you think about the natural log function, it's going to look like that. So if I'm coming at 0 from the right, that's going to be negative infinity. And 1 over x, if I think about that graph, it looks like this. And if I come at 0 from the right, that's going to be positive infinity. So it doesn't really matter whether it's positive or negative. It's infinity over infinity, so I can do L'Hopital's rule. So that's the limit as x approaches 0 from the right. Derivative of the top is going to be 1 over x. Derivative of the bottoms, negative 1 over x squared. So if I flip and multiply, I have 1 over x times negative x squared over 1. So one of the x's cancels. So now I e both sides. Nope, sorry. I plug in 0, and I just get 0, right? So that limit is 0. Now I e both sides, and I get that the limit as x approaches 0 from the right of f of x equals e to the 0, which would in fact be 1. So my original problem is 1 for the answer. Okay? So again, the notation is very important. You have to clearly identify what f of x is before you do any of these steps over here, and keeping everything on the right-hand side allows you to e both sides easily and clearly. So I know that it would take less space if you did a big long equal sign, but then it's not as easy to see that you're eating both sides that way. Okay, next example, 1 plus 2x to the 1 over 2 ln x. So if I plug in infinity, I'll get infinity to the 1 over infinity, so infinity to the 0. Again, that is one of our forms, so I will identify f of x is 1 plus 2x to the 1 over 2 natural log x. So I'll ln both sides, and I'll bring this 1 over 2 ln x out in front of my ln, and then I put my limit in front. So now I rewrite the right-hand side, be the limit as x approaches infinity of the natural log of 1 plus 2x over 2 natural log x. If I plug in infinity now, I will get the natural log of infinity, which is infinity, over infinity. So I can use L'Hopital's rule. So I have the limit as x approaches infinity. The derivative of the top is going to be 1 plus 2x on the bottom and 2 on top. The derivative on the bottom is going to be x on the bottom and 2 on top. So if I flip and multiply, I get 2 over 1 plus 2x times x over 2. The 2's cancel. I still have infinity over infinity, so I can do L'Hopital's rule again. So that'd be the limit as x approaches infinity of 1 over 2, which is indeed 1/2. So now when I e both sides, I get the limit as x approaches infinity of f of x equals e to the 1/2, which of course would mean the square root of e, which would be my answer up here. Okay? 2 more examples. I'll move over here to the left on this one. So f of x I'm going to identify as 1 plus x to the 1 over x. Natural log both sides. And that is coming at 0 from the right. That would be because I'm not getting to 0, I'm approaching 0 from the right, so that's in the domain. Anyway, I can bring the 1 over x out in front of the ln, and then I take the limit of both sides, and simplify the right-hand side. So that'll be the natural log of 1 plus x over just x. And if I plug in 0, I will get natural log of 1, which is 0 over 0. So I can use L'Hopital's rule there. So the derivative of natural log of 1 plus x is 1 plus x on the bottom and 1 on top. The derivative of x is 1. So now when I plug in 0, I get 1. E-ing both sides means my answer is e to the first. So the limit as x approaches 0 from the right of f of x is e. One last example. How about x to the 1 over 1 minus x? If I plug in 1, I get 1 to the something getting very, very small, so that would be 1 to the infinity. So I define my function to be x to the 1 over 1 minus x. I take the natural log of both sides. And then I take the limit of both sides. So simplifying the right-hand side, I get the limit as x approaches 1 from the right of the natural log of x over 1 minus x. So the natural log of 1 is 0. 1 minus 1 is 0. I can do L'Hopital's rule. So that's the limit as x approaches 1 from the right of 1 over x over negative 1. If I plug in 1, I get negative 1. And e-ing both sides means I'd get e to the negative 1 for the limit as x approaches 1 from the right of f of x. And remember, e to the negative 1 was really 1 over e, which would be my answer to my limit. Lastly, I've given you a summary here of how to work indeterminate limits. And remember that L'Hopital's rule only applies when you have 0 over 0 or infinity over infinity. So if you have another form, you have to either use algebra or logarithms to get it to be of the form 0 over 0, infinity over infinity, and then you can use L'Hopital's rule. We'll practice some problems in class tomorrow, and hopefully this will make sense to you.